Good afternoon, everyone, and happy Pi Day to everyone. And one little fun fact from this, though, is that it's Pi Day because it being March 14th or 3.14, but Ian Smith came in earlier and also pointed out that the seminar happens at 3 p.m. or 1500 hours, so it's 3.1415.
Nerdiest ever.
So today it's my pleasure to introduce Dr. Trevor Day. Making a journey to Everest Base Camp in 2012, 2016, 2017, and 2018 with future plans to attend Barcroft Research Station on White Mountain in California sounds like a life of a traveling Sherpa. But in fact, this is a description of how Dr. Trevor Day spends his summer months. Well, the highest climb most academics make is to the top of their ivory tower.
Looking down at the unwashed masses?
Yeah, exactly. Yeah. Dr. Day bases a lot of his field research up at high altitude to understand the integration of different organ systems in response to acute and chronic stressors, such as high altitude exposure. Originally trained as a comparative animal neurobiologist, Dr. Day switched his research focus to human physiology when he started at Mount Royal University. Before all that, though, Dr. Day actually started his career as an emergency medical ambulance technician, where he trained at SAIT just down the road. After that, he went and did an undergraduate in psychology here at U of C, followed by a PhD in cardiovascular and respiratory sciences with a focus in respiratory chemoreflexes that he finished in 2007. So to date, Dr. Day states that his most proud scientific accomplishment is building a federally funded research program with a focus on undergraduate research and using undergraduate trainees for that research program. So I think that Dr. Day was being a bit modest because he's also has a couple more impressive things that from one of those projects that the undergrad received an award at the American Physiological Society.
Oh, you dug.
I did. And he also published his research in the Journal of Physiology, which is a highly respected journal if you don't know. But also his research is highlighted in the New York Times on altitude and pregnancy, I believe. Is that correct?
Last year, yeah.
Awesome.
No, I wasn't pregnant. A Sherpa was.
So another noteworthy thing that I thought was interesting from Dr. Day's research is that he goes up to altitude and there he collects some difficult data such as doing blood draws. So for any grad students out there complaining about getting lab time down in the main lab, just be thankful that you have to go up to Everest Base Camp to get your data. And I'm sure if you have a problem with that Dr. Day is willing to take some volunteers for his research collection.
Oh, God.
So in addition to Dr. Day's passion for science, he also loves music, and he's a musician himself. Every year he gets to combine these passions at Calgary's Beakerhead Festival, where he plays in a house band. He does rhythm guitar and also vocals. And he also works alongside veteran science broadcaster Jay Ingram. So today, Dr. Day will present on cerebral blood flow regulation during incremental ascent to high altitude, effects of superimposed hypoxia and hypocapnia. And because today is Pi Day, I'm sure his presentation will be a slice.
Michael Anderson, ladies and gentlemen. I'm just going to hide here behind the pie. Thanks for the generous introduction. That was humbling and fun and weird all at the same time. Not you weren't weird, but it just felt weird. As someone who did some background research, that there's actually something to find these days. So it's amazing how far and how long your career can come before you know it in the snap of a finger. It's great to come back to my alma mater. I actually took environmental physiology from John Kolb here in 1998. Aaron Tubman taught me exercise physiology in like 1997, 98 as well. So it's been a while since I've been back here. I actually gave a seminar last semester as well. So it's kind of fun to break the silo down between Mount Royal and UBC and let's build a bridge across the river. I'm going to try and play it straight and talk about some science today, but I'll throw in some pictures of high altitude as well as we go. I should start with this because, anyone that's a principal investigator knows that you're nothing without your collaborators. You're nothing without your funding agencies, but in particular, you're nothing without your trainees. And so it's really important to thank collaborators and trainees from universities around the world, funding agencies that have helped fund these expeditions that have gone on a number of years that that Mike was telling you about, some industry partners that help make it happen, and of course we need ethics and participants to make it happen as well. So we played nice in the Nepal sandbox as well as our own institutional ethics board for this, and that's really important to do that. So I'm an integrative cerebral vascular cardiorespiratory physiologist. What the hell does that mean? I'm interested in how the lungs, heart, and brain talk to each other, and lately we've added the kidneys to it as well. Of course, I've done it in yellow for you. And so we've done some urinalysis and interested in acid-base responses, and we published, as Mike said, we published some stuff in the Journal of Physiology just late last year around acid-base responses to high-altitude ascent. So that's kind of where my interest lies, particularly in response to stressors. So I don't really do exercise stress as a stressor, but I'm interested in other kinds of stressors like high-altitude physiology. So this is one of my loves, and I fell in love with this when I took John Kolb's course here in 1988 or so. You'll recognize this is Everest right there. This is the Nuptse Wall. The Lhotse face is just in behind. I want to point out Lobuche here, and we'll come back to this mountain. So remember this pyramid-shaped mountain, because I'm going to take you there in a couple of minutes. But this is, I didn't take this picture, obviously. This is taken from an airplane from kind of the south side, and so we end up kind of going around the corner, and Everest Base Camp is just around the corner, and then the summit bid from the south side is just up this way here. And so this is Sagarmatha or Chomolungma, depending on which side of the mountain you're on, in the Tibet-Nepal range. It's just under 9,000 meters, just under 30,000 feet. It's about a third of the available oxygen. Of course, it's 21% all the way up, but 21% of less atmospheric pressure is less. And so it's about a third of the available oxygen at sea level. You're dying up there. It takes you months to get there if you're going to at all. And if you are, you watch birds exercising overhead. That's really weird. But really for us, this, coincidentally, John West says, who's the kind of the grandfather of high altitude physiology, says that this is coincidentally the highest point. It is the highest point we can go to because it is the highest point on Earth, but it's also the highest point that we probably could go to. That if Everest was any higher, we probably wouldn't be able to summit it. Of course, my question for him would be, well, for whom, doing what kind of activity? And we did some research on a pregnant Sherpa who trekked to base camp a couple of years ago, and that's a remarkable human achievement. While 7 months pregnant. So maybe you're wondering why is high altitude a stressor? Well, you're all familiar with diving, I think, right? So, the density of water is about 1,000 times more than air, but as you descend below water, every time you do 10 meters or so, you add another atmosphere because of the density. And we all experience that sensation when we dive, but it's really the opposite effect is true when you ascend to altitude. Of course, the top of Everest is still a third of the atmosphere left because the density is a lot less than water, but it's just the inverse of diving, that as you ascend, the atmosphere thins, there's less atmospheric pressure around you because the atmosphere is density and gravity acts on it. So there's a column of water above me when I descend, when I dive, and that exerts pressure on me, and more the deeper I go. Similarly, when I ascend to altitude, there's less of a column of air on top of me exerting its pressure. So less atmospheric pressure, 21% oxygen of less is less generally, right? So here's Tenzing Norgay and Hillary climbing Everest for the first time in 1953. And they're doing it with supplementary oxygen because they needed it. So this is just from a little textbook chapter that I wrote. You can see here, as we ascend in kilometers on the x-axis, gas pressures changing inversely. There's atmospheric pressure, taking a dive there. 21% of every one of these numbers is here in terms of oxygen amount, the PO2. Our friends in Vancouver, here we are in Calgary, about 1,100 meters or so. An airplane cabin is pressurized to the equivalent of about 2,400 meters, and then all the way up to Everest, about 9,000 meters or so. Coincidentally, Everest Base Camp happens to be about the place, around 5,500 meters or so. It's actually 53 there. That's about half the available oxygen of sea level. So that's a nice kind of tag point to study. Well, the problem, of course, is that there's an oxygen cascade. Even if I hyperventilate, my alveoli will never approach atmospheric oxygen levels because there's dead space and water vapor and CO2 in there displacing the gases. So it's 160 up here at sea level. As soon as I breathe it in, I displace with water vapor, get down to the alveoli. I might get down to 100 or so. And as I, with convection, head all the way down to the mitochondria, that little metabolic Pac-Man that's chewing oxygen up to make energy, is the oxygen sink. And it's useful to think about source, atmosphere, and sink, where you dump it with respect to oxygen, the oxygen cascade. Of course, CO2 is the opposite way around. The source for CO2 is the mitochondria, or cell respiration in the cells, and the sink, of course, is the atmospheric pressure. But we'll focus on oxygen today. But if your starting point, this is Vancouver, if your starting point is a little lower, then you can see that the cascade can really get you in trouble with respect to cellular metabolism. maybe you're wondering, who cares? This all sounds very esoteric. Great, you get to go to Everest Base Camp. You know, you got your federal grant to pay for that. Congratulations, Trevor, nice life. But perhaps this might have wider application, or perhaps not. Anyone who writes a grant in basic science knows they have to try really hard to try and make it sound relevant to granting agencies and perhaps the public. There's an argument to be made that understanding hypoxia as an independent stressor might help us understand when there's comorbidities in hospital. You know, we wave our hands a little bit about that. Sometimes I agree and sometimes I don't agree. But that's perhaps an application to understanding low oxygen. But of course, I think there's lots of popular misconceptions about low oxygen as well. This was taken at the Calgary airport. I was on my way a couple of years ago to Ireland, and I saw this. And it's like, in our own airport, we've got an oxygen spa. You know, you're 96% saturated right now. Knock it off. You don't need to smoke strawberries and feel good about yourself, because it's a waste. Some people think that drinking oxygenated water is a good idea. The last time I checked, the stomach wasn't a gas exchange organ, so you're also just making expensive burps, so knock that off as well. But you know, I think low oxygen has effects on all tissues and really is integrated physiology at its finest. And that's why, to me at least, as a basic scientist, this is so interesting to me. Okay, so one of the overarching questions in high altitude physiology is who gets mountain sickness and why? It's still a bit of a mystery to figure out. I can't look around the room and say, Martin, you're going to be fine. Jarrett, you're in trouble. Like, there's no way of knowing ahead of time. There's no battery of tests. You know, there's a couple of hints that maybe the hypoxia-ventilator response at sea level might be important, but as you ascend, those things change as you acclimatize. So it's really difficult to know in advance who's going to get sick and why. There's not really a fitness aspect to it. There's not really a sex aspect to it. There's not really an age aspect to it either. The years that I've gone, we sent 2 people down with pulmonary edema, and they were both young men, fit young men. And I, as a middle-aged, semi-obese middle-aged man, I'm fine at altitude, and that's weird. You wouldn't predict that. And so that's the big question, is who's going to get sick and why? And imagine if we could solve that question and come up with a test or battery of tests at sea level to perform on people. It would have tremendous application for trekking, for climbing, and for military expeditions as well. So let me just tell you a bit about that. You have a local expert in the room. Martin's in the room and helped publish some of these new guidelines, but I'll tell you a bit about acute mountain sickness as a self-reporting scale. So it's qualitative. It's a Likert scale. It's incredibly flawed for this reason, but it is kind of a clinical tool that tells us a bit about how you're doing generally as you ascend to altitude. The first cardinal sign is headache. As you can see, it's not a very sharp knife, a 3-point scale, but you need to have headache to be diagnosed with acute mountain sickness. You know, none at all, mild headache, moderate, severe, incapacitating. I've seen people with this before. But again, you know, maybe it's because you just trekked 8 hours the day before and you're dehydrated. And you haven't done that in a while. Gastrointestinal symptoms, well, now you're in a developing country, and I've heard it said that in Nepal you either have traveler's diarrhea or you're about to get traveler's diarrhea. So that's one of the two, or often it's both. And so, you know, there's all kinds of confounding variables here as well. You know, but that's not what we mean. We mean anorexia, appetite, nausea, those kinds of things. So from poor appetite to nausea all the way to severe and incapacitating nausea and vomiting. Fatigue or weakness, you know, this could be because you've been trekking again, but mild fatigue all the way to severe fatigue and weakness. 4, dizziness, lightheadedness. This is the one I experience pretty quickly when I go to altitude. Some people have it quite incapacitating. And the 5th one that is on the old acute mountain sickness scale that was published in 1993, the Lake Louise AMS scoring system, we had difficulty sleeping. You know, the problem with this, of course, and the new guidelines that Martin was a part of publishing have taken this away, because everybody's got sleep apnea to some degree up there, and that's another side interest of mine at altitude. So everyone gets central sleep apnea. But you know, generally people have a hard time sleeping up there. That's probably just a normal sequelae of heading to high altitude and acclimatizing. But generally, this is from the old scoring system with a 5-point scale. You know, 3 each gives you 15. If you've got a headache and something greater than 5, you have severe acute mountain sickness. And this is the publication 2018 that Martin McGuinness was on. We don't have a lot of time today, and moving quickly, I know, to talk about prevention and treatment, but the obvious prevention is don't go. But if you're going to go, there's some really straightforward rules you should follow, like ascending no more than 300 to 400 meters per day, taking a rest day every couple of days or so. Make sure you drink a lot, make sure you eat enough, make sure you're sleeping, try to minimize your exertion. And this is why the young fitty fits get in trouble, because they're used to being ahead of the pack and stay ahead of the pack and then overexert themselves and get sick. And that's often what we see at altitude, is the young fit people get into trouble. And so there's some obvious ways of preventing it. My feeling is that up to 5,000 meters or so, it's mostly behavioral. If you take care of those things, you're probably going to be fine. Above 5,000 meters, all bets are off. You go off a cliff, and you just never know who's going to get sick. Treatment, obviously supplementary oxygen. There's some drugs you can take that we won't get into today. Or descend is the best treatment. And this is serious stuff, and we take it seriously when we do high altitude expeditions. This poor participant in 2016 had a really bad night at 5,200 meters, had some crazy dreams. As a respiratory physiologist himself, he was dreaming about the oxygen cascade and couldn't really sleep, and he was stressing out about his own health. We put him on oxygen for a few hours for some sleep and walked him down the next morning. He had pulmonary edema. This is one of my students at Everest Base Camp in 2016. He was kidding here. I just feel so tired, he said, and he lied down being cute. But this is actually what he looked like at dinner that night as well. And so this is a serious thing that can get people into trouble. In 2017, we sent another fellow down who was a young man with pulmonary edema as well. So there's this sort of cascade of adaptation as we ascend to altitude and acclimatize. You know, if I brought you into the lab and gave you low oxygen to breathe, you'd breathe more. That's the hypoxic ventilator response. We all have it. Some of you are very sensitive. Some of you are not very sensitive. So there's variability there, which is really the norm and not the exception. But there's acute responses. If you spend some time at altitude, depending upon the organ system, you'll acclimatize. You'll make more red cells, for instance. That hypoxic ventilator response gets more brisk. And so acclimatization can take days to weeks. If you were to grow up at altitude, if you had a twin brother at birth and you stayed in Vancouver and he went to the Andes, you look different as adults, right? So there's developmental adaptations that take place. And then lastly, evolution is taking place on various populations around the world as well. So there's genetic differences. But the difficult thing in studying high altitude Sherpa or Andean Highlanders or Ethiopian Highlanders is you don't know which one of these things is going on. They're acclimatized long-term by living there, plus they probably have developmental adaptations, plus they've got some genetic differences as well. So it's an incredibly difficult question to address, which is why I'm not. So, you know, perhaps this seems like a silly question. Is acclimatization helpful? Obviously it's helpful, or is it? And perhaps the reason some people get sick and some people don't is some balance between adaptations or acclimatization that's helpful until it becomes negative and hurts you. So for instance, as I said before, when you get stimulated, your carotid bodies are stimulated by low oxygen, you mount a hypoxic ventilatory response. That's great. That increases the oxygen extraction from the rarefied air. That's great. But in the process, you create hypocapnia or respiratory alkalosis. And that's an acid-base imbalance that can hurt you, probably affects brain blood flow, which we'll get to, I promise. And then there's an acid-base balance problem. Your kidneys will then compensate over time, and you can check out Shea Zubilee's paper in JPhys last year to learn more about that. But so, you know, there's a delicate balance between over-breathing with respect to extracting more oxygen, but then running into an acid-base problem. And to the extent to which your kidneys can help may be part of the problem. This is just a quirk of having a mammalian lung. In brain and muscle, if you're hypoxic, those vessels dilate to increase convective delivery of oxygen. But in the lung, it's exactly opposite. So when hypoxic, it's helpful locally for ventilation perfusion matching. But if the entire lung is globally hypoxic, all of the arterioles constrict. You get pulmonary hypertension, you get leaking, and you get pulmonary edema. And this is one of the things that kills people at altitude, 4,000 meters and higher. So that's no good. But we can't help this. You know, over time, your kidney detects low oxygen and releases erythropoietin, acting on red bone marrow to make more red cells. So you can increase the hematocrit, which is the ratio of red cells to total blood volume. And that increases the oxygen carrying capacity. Great, I can carry more oxygen to liver, to tissues, but now I've made my blood more viscous. And now my blood pressure is high. And now I've got a clotting risk. And then I throw a clot and I have a stroke at altitude. So these are delicate balances. And lastly, this is actually a figure from my PhD thesis. Sleep apnea is universal at altitude. It's worse in some people than others. I've seen people at 5,200 meters with 100 apneas per hour. It's more than 1 a minute. And so this is a typical waxing and waning pattern of hyperventilation, apnea, hyperventilation, apnea. And you can see the oxygen saturation alternating. And that really messes with your sympathetic nervous system. And you get a terrible night's sleep as well. And then you're tired, then you tie the rope wrong, you fall and die. So these are all bad news. So I think the balance, in trying to understand this question, which is, we're really not going to solve it here today, is some delicate balance between adaptations that are useful or acclimatization that's useful that tips over into becoming problematic. So let's, because AMS is largely a problem with the brain and hypoxia in the brain, let's just talk about the brain now, and we'll get into our study, which is brain blood flow regulation at altitude. So the brain is a very greedy organ. Unlike many of you are interested in muscle, of course, but unlike muscle, there's not a lot of storage capacity for the brain with respect to substrates for a metabolic rate. So oxygen consumption is quite high. It takes about 20% of Q cardiac output, and 20% of resting oxygen consumption as well, but it's only 2% of the body weight. So it's a very expensive organ. And of course, I think it's my favorite organ because it drives who we are and what we're able to do in our lives. It's got very negligible energy storage because of that high substrate need that you need masterful regulation. And we do that through a couple of different arterial circuits. And as a biologist, I'm always looking for examples of redundancy where you see multiple pacemakers in the heart, or multiple neurons in the brainstem that control breathing, or multiple chemoreceptors that detect blood gases. These are examples of redundancies in the system that helps protect you when things fail. Well, there's redundancy in brain blood flow to the brain as well. There's an anterior circuit and a posterior circuit, and we're going to talk about some of those differences today. And they both converge on a sort of carousel of blood vessels where the carotids come in and the vertebrals come in and help to make sure that there's enough flow to various parts of the brain. In fact, different animals have different pressure gradients with respect to what parts are perfused by what circuits. So famous little anatomy slide just shows you these various vessels we're going to talk about today. This pulse that you feel in your neck is the common carotid artery. It bifurcates just below the angle of the jaw. I've dissected enough of them out in rats to know where they are. And it bifurcates. And at that bifurcation, it's a small little group of cells called the carotid body that is the oxygen receptor. And that's a topic for a different talk. But the internal carotid heads up toward the circle of Willis in the brain. So there's an external and an internal. And the vertebral artery goes up the cervical vertebra as well. And so about 70% of the brain is perfused by the bilateral internal carotids, and about 30% of the brain and the brainstem is perfused by the vertebral basilar circuit as well. So there's differential brain blood flow to different regions in the brain in humans. And this just shows you where we're perfusing. And so the anterior cerebral and middle cerebral come off the internal carotid. In fact, you know, if I was to block off your carotid arteries, you'd pass out pretty quickly. You've all played that game when you were kids in school, right? Stop it. But you can block off those regions, and that causes unconsciousness pretty quickly. In fact, Jimmy Mitchell did a study here, I think, with Calgary Police, choking them out. Did you read that study in JP? And that's why you can choke people out and knock them out quickly, is because you're cutting off blood supply. At least that's what they showed to the interior portions of the brain. And the posterior cerebral artery is these posterior portions here. Okay, so I just want to do a little bit of math, just because I think it's good for us. Who knows what Ohm's law is? Tell me Ohm's law.
U equals R times I.
Well, V equals IR. Voltage equals I. What's I in Ohm's law? We're talking about electricity. Current or flow, right? And R is resistance. Good. Yeah. So voltage or difference, or the driving force, is equal to flow or current times resistance. Well, you can build that up for water in a pipe as well. So there's Ohm's law. There it is for a single pipe for water in a pipe. Pressure is the volume of fluid in it times the resistance of the pipe. Well, really, we regulate flow by altering the driving force and the resistance. But ultimately, also remember that mean arterial pressure, you know, the total of mean arterial pressure in the body is a product of, at least theoretically, the cardiac output. This is how much your heart is ejecting per minute, per unit time, and the total peripheral resistance throughout the body, which of course can change in various different tissue beds as metabolic demand changes. But if you want to look at it for resistance, then it really gets blood pressure over cardiac output. But ultimately for the brain then, cerebral vascular resistance, we can measure it as MAP, which we can measure peripherally, and we can measure cerebral blood flows, we'll get to in a second. We often talk about it with respect to conductance. So it's just the inverse of resistance. So we're going to talk about conductance today. So when you see CVC in some of today's data slides, we're talking about cerebral vascular conductance built up and derived from Ohm's law, which is cerebral blood flow over mean arterial pressure. So a couple of approaches we take for this kind of work. We have a transcranial Doppler ultrasound machine in the lab. Sorry, we talked about this before and we'll talk about it some more. We don't have a tissue ultrasound, but we borrowed one for this study I'll tell you about. But I'm trained primarily in transcranial Doppler ultrasound. There's a temporal window here. You can feel a little thinning in your skull, and that little temporal window allows you to insonate through the skull to detect velocity of red cells in intracranial conduit vessels. And so here's the transtemporal approach that we use most often. You can get retinal arteries if you wanted to, but that sounds scary to me. And we've done some foramen magnum approaches for basilar as well underneath. And so we use the transtemporal approach, and we can get the middle cerebral artery here. So we just put the probe, and it's the easiest thing to find. You know, you can optimize the signal, and there's some some nuances there and some skills in that, but you can get the middle cerebral artery as blood cells scream toward the probe. And there's some ways of knowing both from an anatomical position as well as what the flow profile looks like, and some functional tests. If I want to know if I've got the MCA, if I do a carotid compression, the MCA will disappear because I've blocked it off, and that's a way of knowing, or one way of knowing that I have the MCA. And this was a nice methods paper that we published in 2011. You can also get posterior vessels as well. We actually measure the basilar in our lab and compared it to the PCA, the posterior cerebral, which comes off of it, and they actually have similar reactivity profiles. That's just interesting for us to know. But we can just point the probe back and down and get either the P1 or P2 segments of the PCA. So we can get both anterior and posterior circuits with transcranial Doppler ultrasound. But there's some problems and some caveats with it, and you have to address these when you're actually using TCD. It measures the velocity or the speed of red cells screaming through a conduit vessel. You can't actually see the vessel. All you can get is a velocity profile and use those functional and anatomical tests to know which vessel you're in. It's great for measuring velocity in large conduits. The majority of resistance is in the downstream arterioles from that conduit you're measuring. And so as they change the resistances with, say, CO2 or low oxygen, then you'll measure that in the conduit itself. But the assumption is that that conduit, the Crowchild Trail, before you branch off into neighborhoods, isn't changing its diameter either. And there's some evidence perhaps that at extreme levels of low oxygen or high levels of CO2, the conduit itself also changes its diameter. So now, there's a bit of a problem perhaps with the assumptions. We may actually be underestimating actual flow using TCD when we're doing blood gas challenges. And that's something we have to address when we publish using this. So given that, some friends of mine in Kelowna, UBC Okanagan, Chris Willey, Kurt Smith, Phil Ainsley is a CRC in cerebral vascular physiology. I've collaborated with them a lot, and they've taught me these techniques. Let me just see if I get no, I can't get the video going. And so I've stolen the slide from them. And we can measure volumetric flow in conduit arteries in the neck, both the internal carotid, as I said before, and the vertebral. And we do so a couple of different ways using duplex ultrasound. So we can actually visualize the vessel of interest, and we can get a velocity profile here. So that's just like transcranial Doppler ultrasound. That's all we get with TCD. But from there, we can actually visualize the vessel and the diameter itself. And from that, we can get cross-sectional area. And cerebral blood flow is a relationship between cross-sectional area and the velocity profile itself. And then lastly, if we want to get global brain blood flow, I can get regional, the internal or vertebral, or I can look at global, which is really 2 times the ICA plus 2 times the VA. There's assumptions about equality of flow between the two sides there. But this is a way of getting volumetric flow, actual blood flow to the brain, and probably is a more valid technique. And so we partnered with Craig Steinbeck and his group from the University of Alberta for this study, had an actual trained sonographer doing these measurements for us. We'll talk more about that as we go. So let me just tell you a little bit about cerebral vascular responses to changes in blood gases. So previous studies in TCD, as to say, which is velocity, only utilize the MCA. And I think we're pushing part of the narrative to try and start looking at anterior-posterior differences. But it's easily incinerated, as I said before. It's got high velocities, easy to get, perfuses most of the brain. The assumption was, it's good enough. That's most of the brain. It's fine. But we've determined and shown the vertebrobasilar circuit perfuses a different part. We know that. And the reactivity profiles of anterior and posterior look to be different, and I hope to convince you that today. And so we're going to show you a study that gives us a bit of a background here with respect to these blood gas challenges. So this is the late Chris Willey, good friend of mine that we lost a year or so ago. This is Kurt Smith. Phil Ainsley is my collaborator at UBC Okanagan. We wanted to characterize both the extracranial and intracranial blood vessel responses to high CO2 or to low oxygen. And we're going to show you that there's some differences in reactivity profiles between anterior and posterior. So this just shows you flow using extracranial vessels. Here's the ICA, here's the VA, jumps out at you, don't you think? Different reactivity profiles with increases in CO2. Here's cerebral blood velocity using TCD, MCA, PCA, also look different. You can see here that it really jumps out in terms of flow. I think the statistical analysis is a bit off because we're different units here, but this is the anterior and posterior there. And so for overall, as well as in different ranges as well. So it looks like, at least in absolute numbers, CO2 responsiveness is different between anterior and posterior. Here's normalized, which is to say percent change or relative. So you can see it actually looks quite similar. But just look at the IC and VA here, they look pretty similar. When you quantify it, that difference disappears. And so it depends how you look at it, which is actually a bit of a problem for analysis if you're an analysis wonk. like I am. So with respect to changes in O2 reactivity, you can see here, this is ICA, there's VA. They look different, not just their starting points, but also their absolute responses. And even in velocity with TCD, same kind of thing. When you quantify it, you really see a big difference there. And similar to CO2, when you normalize it, those differences look to go away. In fact, it's a bit of a disaster. And so this is a bit unclear. So we wanted to investigate this a bit more, this sort of oxygen responses in anterior and posterior cerebral circulations. So what have we learned so far before we get into today's study? The brain is perfused by an anterior or carotid and posterior, the vertebrobasilar circuit. They both have reactivity to increases in CO2 or decreases in oxygen or hypoxia. There's differential CO2 reactivity and regional differences in O2 reactivity as well, but that's perhaps less clear. But the problem is this: that's lovely when you're changing one blood gas at a time, but ultimately these things often happen in concert with each other. So what about when when gases change simultaneously? So here's the problem. You're all familiar with laboratory experiments. Yeah, they're hard enough. But they allow for well-controlled and isolated perturbations or stimuli, which is important. We try and get that right in laboratory studies. But in real-world scenarios, like you're hyperventilating or you're breath holding or you're doing high-altitude descent, these CO2 and O2 chemostimuli can actually change in concert concomitantly, and those might have differential effects on these responses. Also, I've been to altitude enough and seen some of these studies done. It's really brutal to give someone hypoxic when they're already hypoxic. And that sounds like a bad idea. And it's dangerous, it's difficult, you need gas tanks and computers and feedback controllers, and it's really unrealistic for fieldwork contexts. And then lastly, perhaps what my brain blood flow is right now, not in response to a small increase in CO2 or a small drop in oxygen, but what's going on right now, it really does, it really demonstrates the sort of metabolic matching that I'm doing at this moment. And perhaps that steady state brain blood flow response to right now is actually what matters the most. So I got interested in this back in 2012. This is the Italian Pyramid Lab. Has anyone been here before? This is just around the corner, spitting distance from Everest Base Camp at 5,000 meters. The Italians built it in 1990, I think it was, as a research station for environmental stuff, where they farm it out to physiologists and physicians. There's that pyramid-shaped mountain I was telling you about, just around the corner from Everest Base Camp itself, called Pamori, and it inspired the architecture of this building. There's a kitchen down here, there's a dining room, there's bedrooms and bathrooms, and then 3 or 4 floors in the lab as well. So we went in 2012 as part of Phil Ainsley's expedition and did a truckload of studies on brain blood flow regulation and exercise and other things as well. So as we ascended, this is Chris Willey, Kurt Smith is over here, and we published a paper in Journal of Applied Physiology during incremental ascent and then staying at the lab for a couple of weeks. And this is my first foray into brain blood flow measurements, and I'll show you my contributions. There they are there, measuring end-tidal CO2 and oxygen saturation, huge contribution. But I helped out with this study, but you can see that with ascent, so starting in Kathmandu, going up to a village a few days later, heading up to another village about 6 or 7 days in, and then staying at the Pyramid Lab across a couple of weeks, you can see that these blood gases are changing, at least measured at the mouth or at the finger. But this is the interesting part, don't you think, where there's dynamic changes as oxygen levels drop, your hypoxic compensatory response causes you to blow off CO2 and you become hypocapnic, right? And that's what we see there. And then we see these changes in brain blood flow. And we only measured anterior in this study. So there's one thing that I wanted to fix with the study I'm about to tell you about. And so you can see here, brain blood flow goes up, but not much during incremental ascent. And then as you acclimatize, it really starts to go up over time. So I want to focus on this part because I think, this is interesting, but not much is happening, at least from absolute values. But you can see that blood gases are changing together at the same time. And this is a bit of a confound and difficult to analyze. And so we wanted to try and think more closely about that. I don't know what we were doing here, but we wanted to look at changes in oxygen saturation and brain blood flow. Those of you that are stats wonks know that this is stupid because this is multiple people. I'm in here 5 times, other people are in 5 times. So we're breaking statistical rules about Pearson correlations, but there's a pretty good correlation that's probably an altitude-dependent effect. So we wanted to get this right. The other problem is CO2 is not even in here, right? So there's some things missing from this story. Okay, so what's the solution? Perhaps we can quantify cerebral blood flow and indexing it against both simultaneous changes in CO2 and O2. And so we call this new index steady state cerebrovascular reactivity. And we're going to do this during ascent to high altitude in the Nepal Himalaya. So let me just take a detour to try and distract you from the data that's about to come, in part because I've never told this story live before. It's probably showing, but also because it's in review. And we're writing the rebuttal letter right now, and I'd be really curious about getting your feedback. But perhaps I want to distract you from it a little bit and tell you a bit about Nepal generally. So people often ask me, well, why Nepal? Why not the Andes? Or why not somewhere else? Why not go to a lab in California, for instance? Well, the incremental ascent model is unique. I've been to Nepal before. I have contacts there. You get quite high, 5,000 meters, but you get there slowly, so the risks of getting sick are actually minimized. It's a bucket list destination that people will self-fund to go to, and that's useful when you're a poor, starving scientist trying to make a research program go on a small federal grant. You know how big those can be, or how small those can be. And this is what it looks like in this region. So it's a lovely place to go and do this kind of work, and there's power in lodges, so you're not camping. There's restaurants. It's a perfect place for this kind of thing. Well, it's not perfect, but it's a lot better than camping on treks. So Everest Base Camp itself is a tent city that emerges every May, at least on the south side. There is a fall climbing season as well, but it's not as popular. So most of the trekking, 40,000 people a year go to Everest Base Camp. It emerges every May or so. This is taken in 2016. By the way, Lintrin in behind here, where a piece of the glacier fell off and washed across Base Camp in 2015 and killed 19 people. You may have heard that story. It's just in the background. So this was taken at Base Camp in 2016. It takes about, it depends on how fast you want to go. You shouldn't do it in 7, but if you take up to 10 days, that's probably fine. And you go from 2,800 meters to 5,000 meters over about 10 days. And so the risks of getting sick are a little bit minimized. And so in 2017, we put a team together of 31 people, including 12 paid Mount Royal trainees. The grant writing just about killed me. And co-investigators from around the world. We had clinicians. We had Peter Andrus, who's a clinician from the University of Alberta, bring the NIRS unit for the cerebral oxygen measurements I'm going to show you. We had a sonographer from the University of Alberta make the brain blood flow measurements I'm going to show you. And we did a stack of maybe 15 different studies. And we incrementally ascended from Kathmandu at 1,400 meters, kind of about the same altitude as Banff for Canmore, all the way up to Fairshea, which we don't really have anything at that high in the Canadian Rockies. And there's a village there at 4,200 meters. And the study was to study cerebral blood flow regulation during ascent. And here are the measurements we made. We used duplex ultrasound, as I showed you, peripheral neck blood vessels for volumetric flow. We measured blood pressure with a phenometer to calculate conductance and map and conductance. We measured arterial blood gases, which normally we just measure them in the mouth, as I showed you before, or a pulse oximeter here. We actually measured arterial oxygen and arterial CO2. And then lastly, we had an NVOS NIRS unit to look at cerebral oxygenation. This is my first foray into this, so you're not allowed to ask questions about it. So here's incremental ascent, a profile. So there's days of altitude exposure. We started in Kathmandu. In some cases, we started some measurements in Calgary as well. Calgary is about 1,100 meters. Kathmandu is 14. We grouped the data together for baseline. And we worked our way up toward Namche at 3,400 meters. I'll show you a picture in a second. That was after the one night altitude there. We made measurements. And then on day 7 at Fairshea at 4,200 meters, we made measurements. So we have 3 different measurements over an incremental ascent of 7 days to show you. So we flew into the most dangerous airport in the world. This is Lukla at 2,800 meters. It's a remarkable place. There's a ledge there. Sometimes planes hit it. In fact, a couple of years ago, the very plane we were on 2 days later crashed there and killed 2 pilots. So it's actually a really kind of frightening story. But it doesn't happen that often. There's the tower. Risk Services loves these trips. And so we fly into Lukla and start the base camp trek. This is at 2,800 meters, about the same altitude as the mountains around Canmore and Banff. And then we start the trek, just to give you a perspective on that. So here's our team at Lukla, ready to start. This is where you start and end the base camp trek. And there's our team of 31 people, and off we go. There we are in Namche in day 3, doing a group shot actually on the way down, some cheating here, but that's the view out of my bedroom window. This is what I get to do for a living, everyone. So I love this shot, and I love this village. It's the administrative capital of the region of the national park. And then from there, you think these are big. It just gets bigger still. And so there we are in Fairshea, about to head up even higher. There's a lot of big smiles here that go away after the next couple of days. But this is where we finished our study before we went up. But I'll just tell you the rest of the story to base camp. Up we go to the Pyramid Lab to visit it again. It was quite emotional to be back there after a couple of years. Still some smiles. And then around the corner, that Pomori Mountain is in the back here. And there we are at Everest Base Camp. There's Lintrin right there. That's the glacier, or parts of that glacier fell off in 2015. And the ice falls are right there heading up. The next morning, we went up to Kalapatar. This is the highest I've ever been at 5,600 meters. You can see Pomori in behind here. There's our lead guide, Nima. A couple of the word Sherpa is not a job description, by the way. It's an ethnic group. They just happen to work in tourism. So here's a couple of our Sherpa guides overlooking the Everest region. You want to see what it looks like from here? The view across the valley is that. So there's Everest Base Camp. There's the Ice Falls. And then you go between the Nipsey Wall. Lhotse Face is right there. And then there's the South Summit toward the summit there. And Tibet's just around the corner on the other side. So this is why you do this kind of stuff. So you don't need, we're done, right? We're good? You don't want to see data? All right, so quickly with data. So what we aim to do is characterize the integrated steady state cerebrovascular response, this new metric we've invented, and see if it's any good, and see if it actually makes some sense to quantify brain blood flow this way. Our hypothesis was that our metric would better track, that this metric takes into account CO2 and O2 simultaneously, would better track the response during ascent. We thought there'd be regional differences, which was a bit unclear from laboratory studies or a bit messy, and that we thought cerebral blood flow would be related to oxygenation. Perhaps that was an obvious question, but we weren't sure actually how those measurements would work out. So these are our stimuli. Here's PaCO2, and the reason I do this first is because it's going to matter for a metric in a second, but ultimately, as you ascend in altitude, day 0 in Kathmandu, day 3 in Namche at 3,400 meters, day 7 in Farache at 4,200 meters, you can see that there's a drop in oxygen, but you maintain because of acclimatization and the ventilatory response. That decrease in oxygen and that ventilatory response that results drives CO2 down and creates a hypocapnia. So there we are in Kathmandu, and these are arterial CO2 levels and arterial oxygen saturation. You can see that CO2 also comes down. And when we index this against that to create what we call a stimulus index, a steady state stimulus index, we get this. And so although it looks like there's no change with ascent, there might be a trend there, but individually there's a big scatter there. And so we want to use this to index brain blood flow. And this is how we calculate it. Okay, and this is in review now, so we're writing the rebuttal letter as we speak. Well, not actually as we speak. So here's the cerebral blood flow response. Remember we talked about the ICA and the VA. There's more blood going to the ICA than the VA. Global is here. So there's your Kathmandu or Calgary measurements there. As we go up to Namche, it looks like there's no change, at least statistically. But in Farache at day 7, there was a statistical difference. Star means greater than baseline, okay, from now on. When we use our new metric, when we index cerebral blood flow against the SI, you can see that more differences pop out. And so, yes, we're still different than baseline, but the cross means different than the previous altitude. So it looks like we tracked the cerebral blood flow response a bit better by indexing it against both blood gases. When we looked at conductance itself, this takes blood pressure into account, if you recall. You can see that, again, these are different than baseline, and then more differences pop out. Sorry about this. More differences pop out. These are all crosses, by the way, different than both baseline and the previous altitude. So it looks like conductance with this stimulus index worked better as well. So both what I call the SSCBR, steady state cerebrovascular reactivity, and the conductance side of it better characterize these responses with altitude, it looks like. What about regional differences then? So here we are with actual absolute deltas. This is the ICA and VA. What we did here is compared Calgary or Kathmandu to 4,200 meters, right? So what happened over those 7 days in terms of brain blood flow? Well, the ICA, it was quite a big response, but a lot of variability, as you can see. The VA, a much smaller response. This was 0.053, so maybe you could say not difference if you want to play a hard line. But in the percent change, much like previous studies, no difference. And this trend is going to come out all the way down. So if we look at our new index, steady state chemo reflex drive, it actually came out quite different between ICA and VA. Normalized, no difference. In conductance, big difference in absolute, not in normalized. And lastly, in the steady state conductance, when we normalize it against the SI, big differences between anterior posterior, not with percent changes. And so it looks like in absolute values, the answer is there are anterior posterior differences with respect to oxygen responses, and no one's looked at it this way before. But if you do it against a percent change, the differences aren't there, much like we've seen before. So there are regional differences in brain blood flow responses to ascent. And lastly, what about oxygenation? Perhaps this is intuitive, but we weren't sure what we'd see. So here we've got arterial oxygen content. Here's how we calculate it. So we take the amount of hemoglobin that you've got. Of course, you're making more over time as you ascend. We take the saturation of PaO2 and plug it into this to get content. You can see that it actually goes down, but it's protected as you acclimatize, likely because this is higher after 7 days. And these are different or lower than baseline. And then lastly, when we look at cerebral oxygen saturation using the NIRS device, we call it regional saturation, anterior portions across the forehead and the brain on the same side as the ICA we measured, just so you know. You can see that that actually decreases as well with Ascent. But it's again protected here and doesn't get much worse after 7 days. But then when we correlate just at the highest altitude where people's oxygen saturation is lowest, so here at 4,200, here at 4,200, we look at the ICA, anterior vessel, going into the brain. This is at 4,200 meters. You can see there's actually pretty good correlation. An R value 0.64, statistically significant. But when we index it against our new SSCVR, it's actually a better fit, 0.79. So that's a strong correlation. It goes from moderate to strong. Looked at raw conductance, not bad. And then we index conductance against the SI, and we're a really strong correlation again as well. So it looks like regional saturation using the NIRS device, brain cerebral oxygenation is well correlated with our novel indices, better than just looking at brain blood flow by itself. So what have I told you here today? We've developed a novel metric of steady state cerebral vascular activity that indexes brain blood flow against both chemostimuli, the change in CO2 and the change in oxygen at the same time at the steady state, not in response to a perturbation. And we demonstrated regional differences that haven't been shown this clearly before with respect to oxygen responses. And lastly, this novel index was better correlated with cerebral oxygenation than just brain blood flow by itself. What's next? This is the Barcroft lab, as Mike said when we started, on White Mountain in the Sierra Nevada mountains on the eastern border of California. We're going to fly into Las Vegas, behave badly, rent cars, drive up to the lab for 9 or 10 days, do a bunch of studies around sleep and a bunch of other brain blood flow regulation studies as well. And what I really want to do is kind of develop a grand theory of everything. To what extent does acid-base responsiveness over time link to brain blood flow changes over time, and how does that link to sleep and the incidence and severity of sleep apnea over time? So that's the main study that I'm going to be doing at the Barcroft lab, which sleeps about 24 plus a staff. There's a kitchen and they cook for you. So we're going to do that this August. So with that, I got a little longer than I'd hoped to, and I know I'll move fast, but thanks for coming, everyone. One of my favorite pictures of Everest in the back there, taken by a photographer, Ken Emery from Calgary. So thanks for coming.
There's gotta be some.
That's why I went long, just to limit this part.
Yeah. So Martin, at the back.
Oh no, local expert. You're not allowed, Martin.
I don't have any hard questions. Thanks for the talk.
Good, good.
Every time you show pictures, it weakens my resolve of never going back in the hall just a little bit.
Good,
a little
good.
closer to wanting to go, but
Yeah.
I still don't want to.
Still don't want to go, yeah.
No. In your studies, we had the incremental ascent.
Mhm.
Do you have a way to try to angle acclimatization from a further ascent? So like the Faraday data versus the 3,500. You know, if you stay at 3,500,
Right.
what happens in the third
Right,
panel?
that's a great question. Well, I don't have those data. In fact, every study I've been a part of and seen from the Okanagan group or ourselves, we just keep going to the Pyramid Lab or go to Everest Base Camp. So we don't have those data. It'd be interesting, I think what you're getting at is, does it continue to go up over time? I mean, what I showed, I think I can do this really quickly. What we showed from Chris Willey's study, sorry to do this to you, from the 2013 J Applied Phys incremental ascent. I think I'm there. You can see here that it didn't really do much, but look what happened between arrival at 3,400 meters and then the next morning, it didn't really go up statistically. So maybe nothing would happen. It's hard to know over time. It'd be fun to actually spend a month in Namche, and we should maybe do that together. Yeah. Type 2 fun.
Yeah,
Fun in hindsight.
okay,
Yeah, I don't have an answer for that. I'm sorry. Yeah.
Okay.
Yeah.
You talked about the viscosity of the blood. Could you again explain when that happened and why?
So viscosity goes up because the drop in oxygen is detected by the kidney. There are oxygen receptors in the kidney that detect the low oxygen. They release erythropoietin, which acts on bone marrow to make more red cells. And when you make more red cells, your hematocrit goes up, and thus the number of solid masses compared to your plasma. Plus, some people get dehydrated as well. You get thicker. The blood gets thicker, and that can make it more difficult to circulate the blood. But also, there's more interactions between red cells, and that can cause risks of clotting. And that's a big concern when we go to altitude. If you have polycythemia and your hemoglobin concentration gets too high, that's a real risk. So,
Have you ever thought about doing something against that viscosity?
like doing a hemodilution study or something like that,
No,
perhaps, or
doing some interventions that they have less viscous blood.
yeah, we haven't played with that at all. Phil Ainsley's group and Ryan Hoyland leading it has recently done some hemodilution studies where they took a liter of blood out and replaced it with saline. And they did those studies in the Andes, and they're actually trying to publish them now. And that's the best I've got for you, but I haven't done any work with that. But it is a real risk, and we worry about it at altitude. In fact, some people go down if their hemoglobin levels are too high because it's a risk.
John.
What type of hematocrit levels are you talking about?
I don't have those data here with me, I'm sorry, but I wouldn't, it's in Shea Zubilee's paper in JPhys. Someone look it up right now. JPhys 2018 Zubilee's et al. We published it in a table, but I don't think we approach 50%. Yeah, the problem is that people do get dehydrated, so it's a bit of a skewed metric because it's both the plasma volume and number of red cells. But I think our data from these blood draws showed that people didn't get dehydrated. Their osmolality is normal with ASCENT, so it looks like it's just a red cell increase. It takes about 7 to 9 days to start to see it in the incremental ASCENT model, at least anyway. And I don't think we got over 50%, which of course is the threshold for, oh, you're cheating if you're a cyclist, or you get into the danger zone with respect to viscosity. But I think we got into the sort of high 40s, if I recall. I'm sorry, I don't remember. Yeah. Hi.
What is the reason that people get dehydrated? Is it because they drink too little, or is this also an adaptation?
Yeah, that's a great question. So the question, if you couldn't hear him, is why do people get dehydrated when they ascend? It's probably a couple of things. One is, when you're exercising more, you're sweating, obviously, but also you're breathing more, and the air is very dry. So it's called insensible water loss. Sweating makes sense because it's thermoregulation, but losing water through breathing is insensible. And there's a lot of water vapor loss just from the act of breathing more into a dry air. So that's one of the reasons. Also, everyone's got Travis diarrhea, and you get anorexia. Your appetite to eat and drink goes away, so people aren't drinking enough. So I think it's all of those things together. We stayed on top of people on our trip, and we managed to keep the osmolality quite similar. So.
But it's not an adaptation, because I've been to about 5,000 meters.
Oh, cool.
Walked up,
yeah.
And I remember that I had to go to the bathroom a lot.
Yeah.
Much more than and I wasn't drinking a lot, but I had to pee a lot.
Really? Were you on Diamox though?
Huh?
Were you on acetazolamide? No, because acetazolamide is a diuretic and makes people pee a lot. So. Really? That's interesting. Yeah. Martin, what's your feeling about that? Do you know people peeing more generally, even without Diamox?
There's a diuretic effect of altitude, and it hemoconcentrates, so it increases content, but how helpful it is,
yeah.
I don't know if anyone's done the plasma volume expansion just for that.
Right.
I know people have done it for like max cardiac output, but just for day-to-day activities, I don't know.
Yeah, it doesn't seem like an adaptive thing to get dehydrated at altitude, but I'm not sure I can help you on that. I think it's just a consequence of all the stressors rolled in together.
Yeah.
So Trevor, you started off telling us about mountain sickness, and you showed us a nice new data set.
Yeah.
Did you try to relate it to mountain sickness?
Yeah, so we have AMS scores in everybody. I can't say I've done the correlation between our metric and AMS scores. You and I may agree in this, but I'm not sure. My confidence in the metric, the AMS score metric, as a quantitative value is quite low. As many of you know, it's qualitative, it's non-parametric, stats are harder. You can't just do correlations. You need to use more Spearman correlations as opposed to Pearson. I've tried correlations over the years with lots of things and not seeing anything. I'm not convinced it's a useful physiological metric to correlate with anything else. I'm not sure what your feeling is about that.
I probably have a lower opinion even than that.
Yeah. It's a snapshot of how are you feeling. That's about it, right? Yeah. So I've moved away from even bothering. I used to run correlations like crazy with everything, and I'm just like, what the hell is this for? Because I'm not convinced it's useful anymore. But I'm glad we agree anyway.
Mike, do you still have a question?
Sure. Yeah.
Don't be afraid, Mike.
Well,
I might regret
Mark's
this.
question was my first one,
Yeah.
but I have
We could answer it again.
Well, it's mainly like how to there's a lot of variability in this, and I guess it kind of comes back to Martin's question of like, who gets acute mountain sickness? Is it related to whether or not you're delivering more oxygen? But you also mentioned there are plenty of other things, like whether it's kidney imbalance or like pulmonary edema.
Mhm.
What's the biggest
Mhm.
factor that generally puts people out? Like the pulmonary edema?
Well, that's certainly a thing that triggers a descent, triggers a medical intervention, and a descent is pulmonary edema or HACE. I've never seen HACE personally. Have you seen HACE? It scares the shit out of me. You've seen HACE? Yeah, it's frightening. Ataxia, incoordination, and consciousness. Not something I want to run into. But I think part of the problem really lies in your question. A, there's too many organ systems talking to each other. All of them have their own inherent variability. All of them have their own responsiveness to acute stressors. All of them acclimatize at different timescales and to different amounts. And then they're talking to each other. So I think that's the problem, is the variability and the interactive nature of all of this is what makes it interesting, but also so hard to crack.
And I guess the follow-up to that would be like, you mentioned that the initial fitness of people doesn't really dictate whether they get acute mountain sickness or not. But this type of stuff would suggest that like if you have a higher VO2, you should do better, right? You're always going to be higher up on you're starting at a higher point.
During exercise.
Yeah.
During exercise. Yeah, but in terms of just sitting at a lodge, if we were at a lodge at 4,000 meters, you suspect you're way fitter than I am. Your VO2 max is 70, mine's 25. I suspect that, who knows? I know that I do well at altitude as long as I do those behavioral precautions. So I think exercising at altitude, that's a different conversation. I think that makes some sense that perhaps your fitness is helpful. But the problem is that then you add intensity to it, and then the young fit people run ahead, and then they're screwed and have to go back down again. So I think that level of intensity of work actually gets you into trouble, even if your VO2 max is higher. So that's a mystery to me as well. But I think in terms of just like my fitness to do this trek, I usually kind of go on a pretty hard 4 or 5 month cycling binge to get ready to go. And I have a better time when I'm fitter. I've done it 4 times now. I've been different amounts of fat every time I've gone. And so certainly your ability to trek every day for between 4 and 7 hours is better if you're fitter. But I don't think there's any relationship there with how well you do just being at altitude. I'm not sure if that's helpful.
Third question,
Yeah.
It is. Is there any protective effect of living, say, in Calgary relative to Vancouver? Like, what's the threshold of having some benefit of living at altitude?
Yeah, no, this is dangerous territory because now we're getting into live high, train low, and all that kind of stuff, which is a mess in my view, and I think a bit worrisome. I'm not, the problem with those tent studies that some of you are aware of is now you've got sleep apnea. So you go ahead and sleep high and try and get some benefits of repeated high sleeps, but then you've got sleep apnea, so you're tired, and that's going to affect your training, right? So I'm not convinced it's as a useful thing in terms of deriving benefit for exercise. That's a long conversation. And I'm not an exercise expert, you are. But I think just in terms of driving benefit generally, I hear anecdotally all the time of people coming from Vancouver to Calgary and feeling that they can't run as well. We're only 1,100 meters, but we're, the atmospheric PO2 is 160 in Vancouver, it's 140 here. So perhaps if you've got lung disease or you're less fit, perhaps there is an effect. Or when people go from Calgary to Vancouver and perform, they talk a lot about it. I've never seen those studies quantified. I don't know, does anyone know of those kinds of really mild altitude studies? I think they're not as sexy, right? Because this stuff is sexy and gets funded and it's easier to kind of sell. But I think you're onto something. I think that moderate altitude question is more interesting and more relevant to more people, whether it's exercise, athletes, or just generally how people do going from Denver to Calgary to Vancouver. In fact, I want to go and spend some time at the Alpine Club of Canada hut, Abbott Hut, 3,000 meters. That's about the cutoff for acute mountain sickness symptoms. I think that's some interesting question to ask around moderate or mild altitude.
Martin, you have a comment for that? You had your hand up.
Yeah, jump in.
The only study I can think of, Trevor, is Usarium has done a moderate altitude residency for protective effects, and I couldn't nail the altitude, but 1,800 to 2,400.
Oh, so low, yeah.
I don't know if anyone's looked at 1,000 meters for protective effects, but if you're living at 2,000, you do better at 3,000. Which makes sense.
Right. So when you go from 2,000 to 3,000, you're better off than sea level to 3,000.
Exactly.
Yeah, fair enough. Yeah, sure, because you are acclimatized. I mean, when I instrument people here, normal and tidal CO2 or arterial CO2 here is 34, not 40 like the textbooks say. I see 85 for PaO2 in the lab all the time in Calgary, or in tidal O2 even. Saturations, are still, some people are in the high 80s when I instrument them. So we're at altitude, mild, but our cardiorespiratory and hemodynamic variables are different than Vancouver for sure. However mild.
Okay, Jared.
Hey.
Just a quick comment.
Not allowed. You were supposed to be on my side, man. We work in the same place.
And I'll start with my question of how we sign up for these bad things in Vegas.
Get a job in Mount Royal and we'll talk. Yeah. Oh, you're already there. Yeah.
No, but I think Robert Chapman's group and Jack Daniels and you with the NAU Northern Arizona has a lot of at least anecdotal evidence. Chapman would have published some of this stuff to say that the difference between similar altitudes of Calgary to sea level would be like 1, 2, 3% over
Right.
a mile or 3,000.
You're talking exercise performance. Okay. Yeah. Yeah.
And then my question related to, you're talking about trying to determine who's going to get altitude sickness. One of the things that we do when we take athletes to altitude to see if they're going to respond or not respond.
Right. Because that's the problem, right? There's variability there too, right?
Right. Is
Yeah.
have them exercise at sea level and look at their saturations, and the ones with the saturation
Right.
tend to be worse at altitude. Has anyone thought about doing
Sorry,
that?
just if you can pause. Worse when they exercise at altitude, or just worse at altitude?
Worse from the exercise?
Okay,
Or that
yeah,
their
right.
performance difference is worse.
Yeah, that sort of makes some sense.
Yeah.
Because if they're desaturs already, and now you make them hypoxic. Yeah.
Has anyone done sort of those sea level exercise to see if they're going to get sick?
I think so, but I don't know the studies. Martin, that's more your wheelhouse than
I'm
me.
blanking on the gentleman's name in France.
Damn it. Yeah,
He has
me
like
too.
a standardized exercise protocol at sea level that he tries to use to predict mountain
Right,
sickness.
right.
Like Richelet, yeah.
Richelet, okay.
Jean Paul.
Yeah.
But I can't remember the results off the top of my head. But someone has tried it.
Hmm. And it hasn't stuck in your head though. Maddie, do you know? I should be leaning on you more too. I'm sorry. Good questions, but I think what you've prompted me today is to really start chasing down those mild altitude studies, because I have an interest in that, and I think it's worth exploring because people ignore it because it's not sexy, but I think it's more relevant to all of us, really. Yeah.
How long of an exposure to altitude are you looking at before you start seeing significant increases in hematocrit? Like, are these 4 or 5 hour exposures that people are doing in tents and things where they drop the...
Yeah, John Kolb published a bunch of that stuff with respect to cerebral blood flow and veterinary stuff, I think, in the late 90s, but I don't know about hematocrit. I can tell you that with this model, the incremental ascent model, I don't really see increases until, 8, 9, 10 days. But again, it's incremental, so it's hard to know. If you just went to 5,000 and stayed there, you might reach a threshold of getting a higher hematocrit faster, but I'm not sure.
Like if you do it for 5 hours a day for a week, are you going to expect to see anything, or do you need a longer exposure period within that period?
Yeah, I don't know. I'm sure that's published. I don't know the answer to it. I'm sure that's published. Because ultimately that gets at this exercise performance thing, right? The whole point of living high or simulating at least sleeping high is to try and get a hematopoietic response to give you an advantage in terms of oxygen carrying capacity during exercise stress. But again, my caution is that now you've got sleep apnea and you're tired. So I think there's a lot of trade-offs that probably take place that some of you would know more than me about.
Yeah, Mike?
I guess in a longer term adaptation, do people who grow up at altitude have relatively higher blood pressure than those who live lower? Do they have an adaptation in
Yeah.
the cardiovascular system to normalize everything?
So I bet Maddie knows more about this as well, but depends on the group. So I can tell you from high altitude descent, the heart rate goes up a little bit and kind of normalizes again. The blood pressure isn't statistically higher at the highest altitude. And that's because, hypoxia similar to the carotid body causes a sympathetic chemoreflex, total peripheral resistance go up, blood pressure goes up, but then hypoxia it's sympatholysis, right? Well, I suppose we reserve that for exercise in muscles, but there's a vasodilatory effect of hypoxia that probably balances out the total peripheral resistance aspect. So I don't see higher blood pressures up there in lowlanders acclimatizing. I think in whatever measures I've done in high altitude Sherpa, really not hypotensive, but really normotensive. But the Andean Highlanders have a different story altogether. They have inappropriately large hematopoietic responses. And I've seen slides at conferences of 70% hematocrit in Andean Highlanders. Because of that, the viscosity associated with it and the pulmonary pressures associated with that, and the right heart failure that happens over a couple of years, they get really bad blood pressure responses. So I think it depends on the group that we're talking about. And that, I think maybe there's a clue in there as well, that Andean Highlanders are different than Sherpa, and Tibetan Highlanders and they're different again than Ethiopian Highlanders, although we're speculating because those studies aren't really well done on Ethiopians. So there's genetic differences or at least, and who knows whether it's acclimatization, developmental, and or genetic in those populations with respect to how they live and reproduce and work at altitude. But lowlanders don't seem to have an increased blood pressure response, at least in my hands.
Any last questions for Dr. Day? All right, let's take a moment.
Thanks for coming, everyone.